Hello students. We have already seen graphical representation of linear polynomial. So now let's see the graphical representation of quadratic polynomial. We also know that quadratic polynomial is expression with highest degree 2. The standard form of a quadratic polynomial is ax square plus bx plus c, where a, b, c can be any real number, but a cannot be equal to 0. Remember, here a is the leading coefficient, that is coefficient of the term which has highest degree, and c is constant term. Let's find out the coordinates of polynomial p of x equal to x square of quadratic equation by converting it into y equal to p of x form, which gives us y equal to x square. And now by assigning different values to variable x, we get different coordinates of the polynomial. You can see when we take x equal to -3 and put in equation and solve it, we get value 9, which is our y coordinate. Similarly, if we take x equal to -2 and put it in equation and solve it, we get value 4 as our y coordinate. And similarly, we can find coordinates of other points also. Now plot these coordinates. Say point A has coordinate -3, 9, point B has coordinate -2, 4, and point C has coordinate -1, 1, and point D has coordinate 0, 0, and point E has coordinate 1, 1, and point F has coordinate 2, 4, and point G has coordinate 3, 9. Now join the points and observe the shape of the graph. Is it straight line? No, it is curved like U. This shape is called as parabola. And note that its mouth is upward on positive side. Here, graph cuts x-axis at 0. Therefore, 0 is the 0 of this polynomial called alpha. Now, instead of x square, let us take -x square. Let's find out the coordinates of polynomial p of x equal to -x square by converting it into y equal to p of x form, which gives us y equal to -x square. And by assigning different values to variable x, we get different coordinates. You can see when we take x equal to -3 and put it in equation and solve it, we get value -9, which is our y coordinate. Similarly, if we take x equal to -2 and put it in equation and solve it, we get value -4, which is our y coordinate. And similarly, we can find coordinates of other points also. Plot the coordinates in the same way as previous case on the graph paper. Now join the points and observe the shape of the graph. We see that graph is reverse parabola. Thus, if the leading coefficient of x square, that is a, is positive, then parabola will be open upwards. But if the coefficient a is negative, then the mouth of parabola will be open downwards. Now let's make task little difficult. We took polynomial with one term. Now let us take polynomial with 3 terms. Say x square -3x -4. Let us see what the graph of polynomial y equal to x square -3x -4 looks like. Let us find out coordinates of polynomial p of x equal to x square -3x -4 by converting it into y equal to p of x form, which gives us y equal to x square -3x -4. And by assigning different values to variable x, we can get different coordinates. You can see when we take x equal to -2 and put it in equation and solve it, we get value 6, which is our y coordinate. Similarly, we take x equal to -1 and put it in equation and solve it, we get value 0, which is our y coordinate. And similarly, we can find coordinates of other points also. Plot the coordinates on the graph paper, just as we did for previous examples. Take point -2 on x-axis and 6 on y-axis. For second point, take -1 on x-axis and 0 on y-axis, and so on. Now join the points. Graph is parabolic again. And we will also observe that -1 and 4 are the x coordinates where the graph intercepts the x-axis. You know that where the graph of a polynomial intercepts the x-axis are the zeros of polynomial. Thus, -1 and 4 are the zeros of quadratic polynomial x square minus 3x minus 4. Students, note that our first polynomial p of x equal to x square has only one zero, that is 0 itself, while second polynomial, that is p of x equal to x square minus 3x minus 4, has two distant zeros, that is -1 and 4. This means that quadratic polynomial can have two or less zeros, but never more than two zeros, that is alpha and beta. Now students, observe these various graphs on your screen. Each graph is parabolic in shape, which means all are quadratic polynomials, but the way they intercept x-axis is different. From the various graphs, we observe three scenarios. Case 1, where the graph cuts x-axis at two distant points, alpha and beta. The x-coordinates of alpha and beta are two zeros of quadratic polynomial, ax square plus bx plus c in this case. Case 2, where the graph cuts the x-axis at exactly single point instead of 2 points, because the 2 points alpha and beta of case 1 coincide here to become 1 point. The polynomial has single zero of quadratic polynomial ax square plus bx plus c. Case 3, where the graph is either completely above the x-axis or completely below the x-axis, so it does not cut the x-axis at any point, and accordingly does not have any zero. So the quadratic polynomial ax square plus bx plus c has no real zero in this case. So now let's conclude what we had seen in this video. The zeros of quadratic polynomial depends on the number of the points of intersection on x-axis. If the graph of given quadratic polynomial intercepts the x-axis at two distant points, then the given polynomial has two zeros. If the graph of given quadratic polynomial intercepts the x-axis at only one point, then the given polynomial has only single zero. If the graph of given polynomial does not intercept the x-axis at no point, then the given polynomial has no real zeros, but it has imaginary zeros which we will study in higher classes.